Cancer is often called a disease of the genome, and it's not a surprise. Next generation sequencing techniques have taught us so much about the disease by looking at individual patients' genomes. We can see the mutations that cause the disease to grow and propagate in the patient, and we can see what processes drove those changes. But that isn't really what cancer can be about. Take breast cancer, the most common form of cancer, in 70% of cases driven by the estrogen receptor. If you look at the estrogen receptor's gene in primary tumours, those patients in early stages, you won't find heavy mutational burden. You won't find large number of changes. You may find it after rounds of treatment in metastatic patients, but in the early days they're not there, because it's the signalling pathway that has been disrupted, not the gene. All the different cofactors which interact with the estrogen receptor, guide it, make it do the right thing at the right time, have somehow lost their correct control. So what we want to understand is, what are the functions that drive the system? Stop looking at the parts and start looking at how they come together. And single-cell sequencing and CRISPR together provide a unique solution to solve that. People have already combined CRISPR and single-cell sequencing to allow us to get huge amounts of data on how targeting individual genes can cause the cell to change its messaging, how transcriptional changes can lead to different outcomes in those situations. What I propose to do is take it one step further. We've now got the technology that we can do multiple perturbations at the same time. And even better, we can do them at different times. So we knock out gene A at time 1 and knock out gene B at time 2. And the gap between that will simulate what it would be like to give a combinational therapy at 2 different time points. And it'll be a combinational therapy that's equivalent to blocking the gene we target. Now if we do this for a whole host of genes, we can start to see how much of an effect the order of a therapeutic has. We can also see, does gene A and gene B, if they're targeted at the same time, does that cause a beneficial or a negative effect? Do they counter each other? So with that programming, we can start to build a model. And this is really one of the key things we've been looking for years. What timing and what combination of drugs will give the best output? Because we know combination therapies are better than monotherapies. We just don't have time to trial them all in the clinic. This, of course, will generate a massive amount of data. And this is where the third really important advancement comes from: modern machine learning. We can use various machine learning techniques to build models that give us insight to how these processes run. And they will let us pull out the combinations that give the best patient outcome, the minimum side effects, reduced toxicity, and greater survival for the patient. Now this isn't going to give us what's going to end up in the clinic tomorrow, but it's going to give us the right direction to go for those new therapies which have yet to be developed and work out where we really can make a difference.